Basic motor controller uses PWM to lower the speed, and that is adequate for some applications. But this doesn't play well with changing mechanical load. Yes, with low PWM duty cycle speed can be decreased, but there is next to no torque available at low speeds. I tried to make a simple speed controller that will adapt the PWM duty cycle based on applied load to achieve somewhat constant RPM. And I did it without adding any sensors to the motor shaft. I have pulled the circuit on the PCB I got from this video sponsor PCBWAY.com. Like name implies, they manufacture PCBs based on your designs, from simple two-layer PCBs to advanced multi-layer PCBs and assembled boards. They also offer services for other parts of your projects like 3D printing, CNC milling and much more. Go check out their website to see the current pricing and what services they offer. For up-to-date information, go to PCBWAY.com. Back in middle school, we used power supplies, light bulbs and DC motors for different kinds of electrical demonstrations. One of the first experiments was attaching light bulb and DC motor together and cranking the DC motor by hand. The motor generates voltage based on how fast it's rotating and light bulb lights up. This voltage, the Back-EMF, is what I'm using as a feedback to determine the relative speed of the motor in this project. Starting point for this project is the usual circuit for PWM controller. One pin is used to output the PWM signal to the MOSFET, which turns the motor on or off. At this point there is no way of this microcontroller knowing the speed of the motor. Now where and how the previously mentioned Back-EMF can be observed in this circuit? Well, I have selected this high side switching circuit with PWM MOSFET, so one side of the motor can always be connected to ground. And I can use microcontroller's ADC to measure the voltage between the motor's connectors. Unless the motor is powered with same voltage as the microcontroller, voltage divider is needed to limit the voltage going to the ADC pin. Now while the MOSFET is on, voltage across the motor is the supply voltage minus the voltage drop over the MOSFET. And when the MOSFET is switched off, inertia keeps the motor spinning and Back-EMF is generated. If motor doesn't spin, Back-EMF is 0 volts. And when the DC motor is powered, it tries to speed up until the Back-EMF fully matches the supply voltage, but because of friction and other boring real-world things, it won't reach that speed. Therefore, Back-EMF will generally be less than the supply voltage, and if there are external forces in addition to this circuit rotating the motor, voltage can exceed the limit of power supply voltage. Now by measuring the voltage over the motor's connectors with the microcontroller's ADC while the MOSFET is off, we can get grasp of motor's RPM. Now let's try how that works. There's one output pin controlling the motor, serial connection for showing the data, and also one analog input. In the main loop, I turn the motor on for a while, turn it off, wait for inductive spike to pass, and then read the voltage on the motor's connector using ADC. To visualize the reading, I'm printing 1x for each 10 of the ADC reading. So 0 to 1023 ADC range will result 0 to 102 x's in the serial terminal. In addition to time these ADC readings and serial prints take, I also have longer delay for this off period as well. So this is basically low duty cycle PWM signal with the ADC reading during the off period. Now in the serial terminal I can see the crude graph representing the speed of the motor. When I add even the slightest load to the motor, speed decreases and motor even stops. But wait a minute, I'm in control of the output duty cycle and I also have a speed feedback from the motor. Now instead of having fixed duty cycle, I can set the target speed or the target ADC value I'm after and let the duty cycle automatically adjust to achieve that speed. Here's the code for automatically adjusting the output to reach the target speed quickly and smoothly. In main loop I turn the motor off and wait for the inductive spike to pass. I don't have an oscilloscope, so I had to make a guess and I ended up waiting for 1 millisecond. Then I take 5 ADC readings and calculate the average. This is a value relative to the current motor RPM. For visualization I have this for loop again, which prints 1x for each 10 of that value. Next is time to actually adjust the output based on the RPM reading. First I calculate how far the target is from the current RPM, and at this point error is relative to the max RPM. I want the error variable to be relative to the max duty cycle, so I need to scale it. Only reason for this is to get more familiar looking multiplier for the upcoming PID algorithm, or actually I'm using PI algorithm. In addition to current error between the target RPM and actual RPM, I also need the accumulated error or the integral of the error. That is achieved by adding current error to a variable during each cycle. And to prevent problems, I limit how large this accumulated error can get. For example, if the motor can't reach the target speed because of the heavy load, the accumulated error would keep growing. Then, if the load suddenly is removed, that built-up error would cause the motor speed to overshoot for a while until it gets used up. Now that I have current error and integral of the error, I can use them to calculate the output duty cycle. Output duty cycle will be the current error multiplied by a constant, usually known as Kp, plus the accumulated error multiplied by a constant, usually known as Ki. This is called PI control. It's like PID, but without the derivative part. To tune this, I first set the Ki to 0 and adjusted the Kp high enough to make motor's response to changing load quick, but low enough to not have significant overshoot before speed settled. But that wasn't enough. It did respond to changing load, but added load also decreased the RPM. This was fixed by increasing the Ki, the integral part. Without it, the RPM sagged, and with too much of it, the RPM actually increased with the load. Both multipliers are specific to this setup. You need to tune them to match the setup in your own project. And here's the final result. At no load, the motor is spinning at constant rate, and duty cycle is quite low. Now when I add load to the motor, the PWM duty cycle increases, but the RPM stays the same as it was supposed to. For applications where physical sensor cannot be added to the motor shaft, I think this way of getting the relative motor speed could work. At least that is my conclusion based on this demo project. I hope this was helpful. Maybe this opened new possibilities for your future projects. See you next video. Thanks. Bye.